Hi, hope everyone's doing okay. Um, can just continue working our way through MicroCOS with the NetBurner. Um, Today we'll actually get started using the operating system. And I'll go through this pretty quickly because I think you'll see that this real-time operating system has a lot of similar concepts to RTEMs that we used previously. The function calls, the operating system calls are a little bit different than those for RTEMs, but certainly we have the same concepts. In today's lecture, we'll actually start talking about task, and then also we'll talk about semaphores, and then um, we'll also talk about mailboxes. Something that's not quite like a queue that RTEMs provide, but is kind of similar to a queue. MicroCOS does have queues as well, and we'll talk about queues and FIFOs next time. Um, so uh, the reference, the MicroCOS reference, library reference, again, if you've installed the NetBurner software, go to the root of your installation drive, and then you should see an nburn directory, and then a docs directory, and then under that, the NetBurner runtime library. So here you'll see the NetBurner runtime libraries, but then there's a separate manual documenting the calls for the MicroCOS library, and that's the one you'll start using now. Actually, you'll be looking at both of these quite frequently. I've already got that MicroCOS library open here in my PDF viewer. I'm using Adobe Acrobat Pro, uh, the free edition. But one of the nice things about the PDF, this particular PDF viewer, is that when you go to the table of contents on the second page, you can click on any of the functions in the table of contents, and then you'll jump directly to that documentation. So again, we'll look at OS Task Create here soon. And then I'll be jumping back and forth between the lecture and the documentation. So continuing with the lecture, MicroCOS was actually first published in a programming magazine in 1992 by John Labrasse. The version of MicroCOS supplied with the NetBurners based on that original version. So a lot of people actually took that version, which was freely distributed, and the NetBurner people did that. I think the Western Digital people did that with an operating system for their drives. They took that original free version and then have since heavily extended it. So there are several versions of MicroCOS based on that original free version. Jean Labrasse actually saw the need for this, so he developed a company called Micrium, and then they distribute a current version of MicroCOS called MicroCOS 2, which is a commercially available operating system. So you'd have to get a license to use it. I think it is free, I believe, for educational use, but we're actually not using that operating system at all. We're using a version based on the original MicroCOS, the original free version that was published in a magazine and then has since been extended by the NetBurner company. MicroCOS is a much smaller, compact operating system than RTEMs. RTEMs kind of provides everything, but requires quite a bit of memory and a fairly fast microprocessor. MicroCOS is actually developed to run pretty efficiently on 16-bit microprocessors, microcontrollers, or systems with a small amount of memory. RTEMs, you primarily need a 32-bit processor to run RTEMs. Okay, so MicroCOS task priorities can range from 1, which is the highest priority, to 63, which is the lowest. Each task must have a different priority. So MicroCOS uses a simpler scheduler, so it doesn't allow round-robin scheduling like RTEMs would. And this is fairly typical of a lot of real-time operating systems, that every task has to have a different priority. Again, that seems pretty restrictive, but in task design, or an application design, it's not that restrictive with a properly designed application. Okay. When the first routine that's run is user main, that starts at priority 10, but by convention you should change its priority to 50. There's a macro definition for that, main prio. So you'll see that in the code. One of the first calls in user main is a call to change the priority and change it to main prio. And then user tasks should be assigned priorities relative to main prio. For example, main prio +1, main prio +2. User task actually should be in the range between 46 and 62. So that's roughly 16 different task priorities that are available. Smaller than are available with RTEMS, but 16 tasks is certainly suitable for a lot of applications. And there are other task priorities available as well. You do have to be a little careful, because out of the the 1 to 63, the 63 different task priorities that are available, some of them are reserved for like the networking task. I think maybe 5 or 6 different tasks are required to support networking. So and you can't use those. So you can refer to one of the include files, constants.h. Again, that's going to be back in the nburn directory, directly in the include directory. You should see the constants.h file here, and you can refer to that to find what other task priorities are reserved. Okay. You have to allocate stack space for each task that you create. So unlike where in RTEMS we do that via configuration and macro definitions, we in MicroCOS we directly create our array that will be used by each of the individual tasks as the stack for that task. And you'll see we have to pass pointers to the appropriate top and bottom of the stack when we create the task. So you'll need a line similar to this. It's a D word, a double word for I think that's actually that's a 32-bit. A word is 16-bit in MicroCOS, and a D word is the 32-bit integer. And then you can call this anything. We'll pass the same name. Here I've called the array task stacks, and the dimensions of the array need to be the number of tasks that you're going to have. So if it's 2 tasks in your application, not including user main. So 2 tasks besides user main, this would be 2, and then the stack size. And there's a recommended stack size, so we'll set this second dimension in our task array to that that size. And then there's an additional thing, and this is an instruction to the compiler that all the elements in this array should be aligned on a 4-byte boundary. That's a requirement for at least the Intel processors, that it be aligned on a 4-byte address. And I broke this up into 3 lines so it would fit on the slide. But in your code, this would just be in 1 line in your C source code. Of course, it doesn't have to be. You could break it up just like this if you wanted to. Okay. Use the OS task create function to create, and then that automatically starts new task. So if you created a task here with a higher priority than user main, it would start immediately. So you want to be careful not to do that. So here the arguments are, the first one is a function to your task code. You can pass a 32-bit data type as an argument to the task. So we've done that with RTEMS, but often this will just be null or 0 if you don't need to pass an argument. And then you have to pass a pointer then to the top of the stack. Remember, stacks work from the a high memory address downward. So this would actually be the end of the array that we created earlier. And then this is a pointer to the bottom of the stack. And finally, the last argument here is the desired priority. So a typical call might look something like this. At the top, we've got our task code. So this would be the prototype for your task code. Of course, you would typically have a while loop inside the body of the function here. And then here I'm setting aside the array for use by our different tasks. Notice the first argument is 2 here, so that means I'm going to be creating 2 tasks. Again, if I'm going to have 4 tasks in my application, this would be 4. I defined stack size here to be user task stack size, which is the recommended size. You could just put the user task stack size directly into this second dimension here. I just redefined it to be something shorter to save myself a little typing. And then notice I've got the aligned attribute. So in my user main now, to create and start this task, the first argument is the name of my task function. My second argument is null because I'm not actually passing an argument to the task. And then notice this third argument. It's supposed to be a pointer to the top of the stack. So this is for the first task. And so the argument here in the first dimension is 0, indicating that this is task 1. Remember, array indices start with 0. Notice that the second argument is the first dimension is also 0, indicating again that these are both pointers to the stack for task 1. And then the second argument here is stack size, which would actually be, 1 past the end of the array. Again, stacks will typically, when you push something on the stack, it first decrements the stack pointer and then pushes the item on the stack. So this is exactly what we want. One element beyond the end of our stack is actually the top of the stack. And then the ampersand will take the address of that array element, which is what we passed to task create. And then the next argument is the bottom of the stack. That's the 0, 0 element. Again, for if I'm having 2 tasks, which I've actually set up this array, my stack array for 2 tasks, and the next task create, I'd have 1 stack size and then 1 0 here as the next argument and pointers to both of those. And then notice here I'm defining a priority to this stack for this task to be 1 above the main priority. So by default that would be 51. And again, this is fairly typical. Then the next task would have main prio plus 2, then the next main prio plus 3. Notice I'm looking for a status return, and I'm only going to continue if the status is OS no error. So again, flipping over to the documentation here, you'll see that actually returns a byte. There's documentation on all the different arguments here that we've gone through, and then it also documents the possible returns, no error if successful, and then the only other possible return is if you try to create a new task with a priority that already exists. So we only want to if I'm checking if there is an error, meaning I didn't get a no error, then I'm going to take appropriate error action. Okay. I will mention that there's an OS simple task create that's a macro that will automatically define a stack for you. It just takes a function pointer to your task code and then the priority. But again, I'm not going to allow you to use that. I want you to actually use the OS task create function instead of the OS simple task create in any of your code. So I won't use that in any of the examples. A task can delete itself with OS task delete. It's common convention though, although in RTEMS we typically deleted our init task. It's common in MicroCOS to actually just let the user main task run to completion. So just run to the end. You know, it doesn't have a while loop. It just actually creates our task and semaphores and anything that we need and initializes them, and then just instead of deleting it as the last thing, just let it return. And you can change, CHAS can change its own priority with the OS change prio command. Again, you'll see that in our user main function. You can delay for a certain number of ticks so put the task that calls this would be put to sleep. We've seen how useful that is in our previous applications. There is a ticks per second micro. So here, if I multiply 5 times the number of ticks per second, and 5 is in seconds, I'll get back the number of ticks in 5 seconds. And so this a call like this would put me to sleep for 5 seconds, for example. OS lock and OS unlock can be used to protect critical sections by disabling and enabling task switching. You know, again, all of this is documented. OS task delete, for example. You know, here's a description: returns nothing, takes nothing as an argument. What was OS change priority here? It returns no priority, and then it accepts the new priority. Are some of the defined default priorities. Again, 50 is the default main priority. You'll see that some of these are a list of some of them that are actually used. Some of the tasks that are predefined and running for you, if you do any networking, use some of these assigned priorities. So you want to stay away from these. You don't use these particular numbers. Again, in all the applications we'll be using, you can use main prio +1, main prio +2. Those are the safe ones to use. Okay. To use a semaphore, there are, I think, essentially 3 calls. Let me look back at the documentation. Go down to you have to initialize a semaphore, then you can post to increment a semaphore, and pend to wait on a semaphore. There's also a OS pend no wait routine that will allow you to wait on it'll allow you to check the status of a semaphore, whether it's available or not, but it does not wait. So let's look at the OS init. In order to use a semaphore, you have to initialize it first. And this would typically be done in your user main routine. Okay, so any initialization should be done there, and I'll look for that in all the applications. So semaphores are associated with a particular semaphore data structure of type OS-sem. So here I'm defining, you know, this is outside of any function, so this would typically be a global variable so that it can be accessed by all tasks. I'm defining a required semaphore data structure. Again, you could have an array of these if you're using multiple of them, or you know, just have ones with different names. Notice in OS init, I pass a pointer to this data structure, so ampersand, and then the second argument here, I'm initializing it to 0, so it's initially unavailable. And then OS init returns you know, a status byte indicating the error, and I want to check to make sure that that's, you know, that no error occurred, that E is equal to 0 on return before proceeding. Is typically how I'd use that. And then OS post, I pass the address of that structure. This will actually release the semaphore or increment it. And then OS pend actually takes 2 arguments. It takes a pointer to the semaphore structure and then a timeout value and ticks. If that second argument is 0, that means we're actually going to wait forever. And again, that's typical. Both these return you know, error status. A mailbox can be used to pass a single 32-bit data item between tasks. So it's like a very limited queue, right? So I can't pass or very limited, very limited queue in RTEMs. I can't pass arbitrary length data or multiple messages, just a single 32-bit item. It can be used for synchronization and to pass, again, simple data. It could be a pointer to an area of memory, though. Okay. So similar to semaphores, you must allocate and initialize a mailbox data structure for each mailbox. So here I'm demonstrating setting aside numbox of these mailbox data structures. And if you're only going to do one, you don't need this array. But here, again, I need to initialize each of these. Let's see, I forget what let me check the documentation to see what that second argument is, because OS mbox init. So you can put an initial message in the mailbox. Is the initial mailbox or null if you don't want to put anything in there initially. So I set it to null or 0 in this case, and then again I would check the error return. And then to post something to the mailbox, again, this doesn't block if it's full. We can check. I think OS mailbox post is actually next. But we get an error return if there's an item already in the mailbox if it hasn't been read yet. So again, you can't actually stuff multiple items in there. So you're going to have to use some sort of synchronization mechanism to make sure that doesn't happen. So here's a pointer to the particular mailbox data structure, and then here's the value that we want to stuff in there. This can be any 32-bit data item. To keep the compiler happy, we need to actually cast this to a void type, and then it returns an error. Now OS mailbox pend returns the item, so it's a little bit different than these other ones that we've looked at in MicroCOS, where most of the other operating system calls in MicroCOS, they return an error status. The OS mailbox pend returns the particular item. So here I've cast the return value to an int. It actually returns a void star type, a void star pointer, but I cast it to an int. So I've set it up here assuming that we're passing integers in this mailbox. And again, the first argument here is the pointer to the data structure. The next argument is the timeout value. Again, this will typically be 0 to wait forever. And then the error status is actually returned in this third argument. So I need to actually pass a pointer. I'm pretty sure this is a byte type because that's been the error status and all the others. That's a pointer to a byte. So again, this is similar to the return arguments we used in RTEMs. So you wouldn't you want to make sure that you've declared a byte error here and then pass a pointer to that particular value. Okay. So I think that's it for today's lecture. We'll look at I think some of the other features that MicroCOS provides next time. I'll have a couple other videos here for today's lecture regarding the exercise, and then also talking about the next project.